Hi, I'm Rex Black, President of RBCS. Welcome to the RBCS YouTube channel. Hey, I hope you enjoy all these free resources that are available here. And do us one favor. We need to keep the lights on and we need your help to do that. So, when you need testing and quality related services, training, consulting, expert services, you name it, let us be one of the bidders on that next job. We don't expect to get all of your business, but we'd like to get a chance. Thanks and enjoy the shows.
On behalf of RBCS, RBCS Australia, RBCS New Zealand, and Software TestWorks, we welcome everyone today to this webinar on testing return on investment. I am Rex Black, President of RBCS, a worldwide testing and quality assurance firm serving clients ranging from small startups to Fortune 20 global enterprises. Since 1994, RBCS has been both a pioneer and leader in quality hardware and software testing. RBCS has offices in the United States, Australia, New Zealand, and Sri Lanka with partners around the world. We deliver insight and confidence to our clients, helping them get quality software and hardware products to market on time and with measurable return on investment. RBCS has a team of international consultants that deliver customized training, consulting, and outsourcing services for companies that are looking to improve their test and quality assurance practices. RBCS has helped hundreds of companies reduce development and support costs while assuring the best quality products are delivered to customers. I'm the author of Pragmatic Software Testing, Advanced Software Testing Volumes 1 and 2, Foundations of Software Testing, Critical Testing Processes, and Managing the Testing Process. I hold a degree in Computer Science and Engineering from UCLA. I'm also past president of the International Software Testing Qualifications Board and the American Software Testing Qualifications Board. Before we start the presentation, some housekeeping notes. You might have heard of Tropical Storm Hermine or Hermina, however you want to pronounce it. I haven't just heard of it, I'm in the middle of it. And that noise that you hear in the background is the sound of rain hitting our office windows at about 35 miles an hour. Since our internet connection and our power lines are suspended from poles, there is some possibility that the pole might go over or the line might be blown down, in which case this webinar will abruptly come to an end. If that were to happen, we will schedule a rerun of it some convenient time in the future. There will also be an evening presentation of this as well, evening U.S. time, and it's possible that that will run if there is a power failure or internet connectivity failure, but that presumes that the power and internet people can get the connections fixed between now and then, which is probably dubious. So apologies in advance if all of a sudden you stop hearing anything and the webinar stops happening. That's blame Hermina or Hermine or whatever the name is, the tropical storm. Now, assuming that we do keep things up and running, if you have any questions during the course of the webinar, please feel free to submit them throughout the presentation via your webinar interface. There's a place for asking questions. You don't need to ask for presentation copies. The presentation is on the web at www.rbcs-us.com. I believe it's on the digital library page. If you are having problems with either the audio or visual components of this webinar, please contact GoToWebinar support. And if for whatever reason you cannot get to the webinar online, or if you're dealing with an unreliable connection, just download the slides, the basic library, sorry, not digital library. Download the slides from the basic library at www.rbcs-us.com. Use the telephone to connect, not voice over IP. And if you try to connect and there's still no sound on the telephone, then that means that we've been the victim of the tropical storm. Okay, so here we go. Today's presentation is on return on the testing investment. So in our assessment and consulting work with clients, I often ask them, what's the business case for testing? And while people pretty much uniformly agree that testing is necessary and does serve an essential business function, people often have a great deal of trouble measuring the business value, and thus they can't articulate exactly what testing contributes. Being in charge of a function with an unmeasured and often misunderstood connection to business value is not a good place to be at any time, and especially during a recession. So this webinar will help you understand how to measure the business value of testing. So one of the first things to remember about testing is that you are not a cost center. You are a savings center. This has been pretty well established over years. There's if you look at Quality is Free, Phil Crosby's book, where he's saying that economic benefit of quality always exceeds costs. Duran and Greena explained something called cost of quality in their quality control handbook, and I will explain to you how that works when we get to that point in the presentation. Not terribly complicated. It's a very well-established technique. Does this hold for software? Yeah, there was a paper back a number of years ago evaluating the cost of software quality that showed that cost of quality does indeed apply to software. You have Campanella in his book Principles of Quality Costs that has a case study of Raytheon Electronic Systems Group, and we always look at this as part of our assessments, and to date we have not found a testing team that costs more money than it saves. It always saves more money than it costs. So testing has a positive return on investment, and it is one that can be quantified. So let's look at how. Now, there are 4 ways that testing can save money. Now, I say can because it is important that you be effective and efficient. It's theoretically possible that the testing team is not saving money if it's very ineffective or very inefficient. But if it is operating effectively and efficiently, then it's going to save money in one or more of the following 4 ways. Either due to finding bugs that get fixed or preventing bugs, finding bugs that don't get fixed but are then known problems that can be managed around, running tests that mitigate risk. There's a risk mitigation value to testing, and some of those risks are potentially quite expensive, and providing information, timely, accurate, and credible information that helps project team guide the project to success. So those are 4 ways that testing saves money, and notice that they are connected to typical objectives of testing. And this is something else to consider. It's good to have well-articulated testing objectives and then be able to tie quantifiable business value to those objectives and then quantify it. So let's look at how you would do that in each of these 4 cases. So we'll start with the ever-popular cost of quality model, sometimes referred to as cost of poor quality. Basically, this is the mathematics behind the often repeated assertion that the cost of a defect tends to escalate the longer it's in the system. Now, the way that you can do this is cost of quality is broken down into 2 types of costs, costs of conformance and costs of non-conformance. So conformance costs can then further be broken down into 2 groups of costs. One is what's called cost of detection, which includes the costs of testing, at least that testing which that you would have to spend on testing, whether you found any bugs or not. I'll get a little more clear as I go along here. Cost of conformance also includes the cost of prevention and true quality assurance. So this is like achieving a certain level of CMMI maturity would be an example of that. Not testing activities. Testing is considered defect detection. Now, non-conformance costs can also be broken down into 2 groups, and basically that's the cost of internal failure, the cost associated with problems that we find prior to release, and the cost of external failure, which would be the cost associated with problems found by customers and users after release. And obviously, non-conformance costs and internal costs include fixing the bugs and retesting. For external costs, it not only includes fixing bugs and retesting, but also things like less tangible things like dealing with angry customers, dealing with damage to the company image, dealing with lost business, and so forth. So testing is a way to reduce the overall cost of quality. And I'm going to show you a hypothetical case study of that. I'll show you a real case study a little bit later in this presentation, but we'll start with a hypothetical to illustrate the point. So for conformance costs, we're just going to look at testing. We're going to look at manual testing, automated testing, and static testing in the form of reviews. We're going to omit prevention costs of quality assurance, because we're trying to analyze the value of testing, so we want to stay focused on a single variable here. For non-conformance costs, we're going to look just at internal and external failure. We're not going to look at any intangibles that might apply, which essentially means that we're really underestimating the value in some ways. So we're not trying to count customer goodwill and damage there too as part of our calculation. Now, in this hypothetical case study, we're going to assume that we've got 1,000 must-fix bugs in each quarterly release. So we're going to release software every 3 months, and there are 1,000 must-fix bugs in that have to be found and fixed at some point, either prior to release or after release. Sorry, we had a particularly big gust here. It was a little distracting. Now, we're also going to assume some bug fix costs, hypothetical bug fix costs, $1 to fix a bug found in reviews, $10 to fix a bug found in program or unit testing, $100 to fix a bug found in testing by in a formal test group, and $1,000 to fix a bug found by the customer. Now, these are hypotheticals, and they will not hold true in your organization, but what will almost certainly hold true in your organization is the multiplicative increase from one phase to the next. That definitely is something that we see quite a bit. Okay, so let's start with the baseline scenario. If you want to calculate a return on investment, it's always in comparison to something. And so, you know, in comparison to what? Well, the baseline is there's no formal testing. All right, so we're not doing any formal testing at all. So there are 1,000 bugs in the product, and let's assume that the developers in their unit testing find 250 bugs. This, by the way, is pretty typical. Unit testing has an average defect removal effectiveness of 25%, according to Capers-Jones. So this is a fairly average type of number. So 250 bugs are found, leaving 750 to go out to the customers. And we see the calculation of cost of quality over there. We've got our cost of conformance, which just includes the cost of testing. We're not spending anything on formal testing, so there's no cost there. We have cost of internal failure, which includes the cost of bugs found in development and test, which is just the bugs found in development at this point because there's no formal testing. And then we have the external failure, which is the cost of the bugs found fixed customer side. It's $750,000. So our non-conformance costs are a little over $750,000, and you know, we're definitely not dealing with happy customers here. I mean, one of the things that's sometimes confusing about cost of quality is it would sort of seem like, well, the higher the total cost of quality, the more we're investing in quality and the better things are. Actually, usually it's the correlation is the opposite, that the lower cost of quality is associated with a higher level of quality in the field because of the escalating cost. And so for $750,000 in cost of quality, we're buying some very unhappy customers. So let's suppose we put a formal manual testing operation in place with an independent test team. So we see the math here. We are investing $70,000 per quarter in costs of detection. So this is the cost associated with just creating tests and running tests once. It doesn't include things like regression testing and other sorts of repeated testing that has to happen after bugs are fixed. So let's assume that the testers now, the developers continue to do their unit testing, still finding 250 bugs, and that's really important. We want to make sure that the product is going to the testers in a relatively mature fashion. So the 750 bugs come to the testers, and they find about half of them. They find 350 bugs. That's a 50% roughly defect detection effectiveness, which is pretty low, but it'll get better over time, as you'll see. Now, what happens then? So 350 plus 250 is 600. So now that leaves only 400 bugs to go out to the customers. I say 400, that's still pretty bad. Yeah, but it's a lot better than 750, which is what it was before. So if you look at this column here, it says manual testing, you can see that our cost of conformance, which is our investment in testing, is $70,000. That's up, but our cost of non-conformance is way down to $440,000 roughly. Our overall cost of quality now, being the cost of conformance plus non-conformance, is about $500,000 on a $70,000 investment. So this is $250,000 reduction in the cost of quality for that $70,000. So that's the net benefit, and so our return on investment is 350%. So that's pretty good. Nobody's getting 350% in the stock market these days. But that actually is not a typical number. We typically see a number higher than that, as I'll get to a little bit later. And certainly the customers are happy, right? So we're spending $250,000 less on bugs, but we've got happier customers. So that's the illustration of what I was saying a moment ago, that cost of quality goes down and quality goes up. Now, suppose that we introduce automation. So suppose we invest $150,000 in getting some tools set up. Now, this could be tool licenses, or it could include, we go get something like Selenium and do open source, and hire some people to come in and work on building the infrastructure and so forth. So that could be the $150,000. Now, the trick here is that you have to amortize this investment, this upfront investment in building these testing frameworks over some period of time, and a fairly typical amortization period is 3 years. So that'd be 12 quarterly releases. So you can see that we've got a $12,500 cost associated with the automated testing column over here. Let me just highlight that so you can see that. That's this column here, and then you see the $12,500. So our total investment is now up to $82,500. And let's suppose that allows us to find about 40% more bugs, which is not an unusual number. You do better regression testing and reliability testing and performance testing and so forth using automated tools of various kinds. So let's suppose that we get now 500 of the 750 bugs delivered to us. So that's where our defect detection effectiveness is now 66%. We're finding 2/3 of the bugs that are delivered to us in testing. And you can see what happens now. So 750 bugs removed by the developers and the testers together, leaving only 250 bugs out to the customers, which is 1/3 of what it was in the first place. So the customers are obviously going to be much happier. And our costs are way down. As you can see, cost of quality is now under $400,000, and our return on investment is over 440%. So pretty good. Now, let's suppose we come to the realization as testers, test managers, that, hey, we actually could do some smart stuff with respect to getting rid of bugs before they even become bugs in the code. So we can introduce static testing. Now, let's say that the development manager, the test manager, project managers, product managers, so forth, get together and they agree, yeah, you know what, let's have requirements reviews and design reviews, and let's make the test guys in charge of those, since it's a static testing activity. And so they do that. So that doesn't necessarily cost anymore. It's just an issue of moment of involvement, making sure that the testers get involved earlier in the project. So we do that. And let's suppose that testers find 150 bugs in those requirements and design specs. Now, first question there, of course, is, well, is that realistic? And the answer is yeah, actually, because again, to refer back to Capers-Jones's studies, about 45% of defects are introduced in requirements and design specs. So that would mean of 1,000 defects, you've got 450 in the requirements and design specifications. And even relatively cursory, not particularly formal specification reviews can easily find a third of those bugs. So a third of 450 is 150. Now, look at what that does to our cost of quality. Something very nice happens here, because you notice that the test team is finding 650 bugs, but the cost is not $65,000. The cost is $50,150, and that's because 150 of the bugs found by the test team were found at the cost of $1. Nice. So now we've got 900 bugs scrubbed out through requirements reviews, design reviews, unit testing, and formal system testing, and perhaps system integration testing, leaving only 100 bugs to go to the customer. So our overall defect removal effectiveness is 90%, which is pretty good. Not that it can't get better, but that's certainly a good number of bugs to find, and obviously a dramatic improvement over what was happening before from a delivered quality point of view. And notice that our cost of quality here, total cost of quality, is down to $235,000 and change, which is quite an improvement, especially considering that we're looking at $82,000 investment. So it's we saved over $500,000 on that $82,000 investment. So that's a 627% return on investment. So very nice. Now, we've been talking so far purely about must-fix bugs, but of course, not every bug that you find has to be fixed. So let's suppose that in addition to the 650 real bugs that we find another 650 that are not must-fix, that are deferrable. Remember, this is a hypothetical case here, but we're going to just assume that. So, some number of bugs often do get deferred. Whoops, pardon me. So you might be thinking, well, okay, we found bugs that didn't get fixed. I mean, why is that valuable? Where's the value in that? Well, pardon me, we're having a little technical difficulty here. The value in the bugs that don't get fixed is, I'm sorry, I'm having a little technical problem. Okay, get that back. The value in the bugs that don't get fixed is three dimensions, if you will. One is that you know where the bug is, and you can actually prevent the user from seeing the bug by basically walling off the buggy segment of the program, right, and make the part inaccessible. And that might be a possibility. If you don't want to do that or can't do that, then you can have release notes or errata sheets or something that say, hey, there's a known problem in this area of the code. Don't try doing this, or it won't work. Or maybe even better yet, you provide a workaround. So if we can come up with a workaround, then hey, that's good. Now, one thing I want to point out here is we're putting a value on something, but we have to remember that this is relative. Must-fix bugs are much more valuable than non-must-fix bugs, and one of the things that we sometimes find in test teams is that they find a lot of trivial stuff early in the process and the more important stuff later, and that's a problem. You want to sequence your tests based on risk so that you're finding the really serious problems first. The other thing that's important too is you do have to recognize the difference between a must-fix and a non-must-fix bug, because if a bug is classified as not must-fix and you identify a workaround for it or something like that, but then the customer said, no, that's not okay, you have to fix that, then you're going to incur an external failure cost anyway. So a good cross-functional bug triage process should be in place to try to deal with that, this potential problem of misclassification of bugs. Okay. So how do we calculate the return on investment for a bug that doesn't get fixed? Well, the way that I have done this in the past is you talk to the help desk or tech support staff, and you find out what the average amount of time is for different kinds of calls. So, if for a known bug, assuming there's some knowledge base that they can access, a known bug, how much longer does that take, or how much shorter is that, than a call for an unknown bug? And then how many bugs, how many support calls per bug on average, which also is something that should be extractable from the customer support databases. And then finally, what is the fully burdened hourly rate for a tech support person? So if we assume that this hypothetical that it takes 15 minutes less to deal with a call for a known bug versus unknown, and that each bug generates on average 5 calls to the support team, and that a support person costs on average $40 per hour in terms of their fully burdened staff costs, then each non-must-fix bug saves $50 when it's detected. Now, notice that this is just looking at the saved time for the workaround and that sort of thing. The preventing a user from seeing a problem or helping a user avoid a problem. I mean, they're not going to call up and say, oh, thanks for the help in avoiding that problem because I didn't have to call you today. So it's a little harder to quantify those elements, but certainly for the calls that can get disposed of more quickly, we can calculate some of the value of the non-must-fix bug. Okay, now notice that there is no increased cost for the to capture this information. Basically, we're already finding the non-must-fix bugs and documenting them, so the investment remains the same at $82,500. But what I've done here is I've calculated for using the $50 figure at the $650 or 650 bugs, found. Then we've got $32,500 as the value of those non-must-fix bugs. Now, I want to put that in comparison. Notice that in finding must-fix bugs, we delivered a net reduction in cost of quality of over $500,000, and for the non-must-fix, the value is only $32,500. So it's an entire order of magnitude less, more than an order of magnitude less. So, clearly focus on finding the must-fix bugs. The non-must-fix bugs are kind of, in a sense, almost loose change picked up off the table relative to the real hard value of the must-fix bugs. But there's more, as television ads used to say. Well, wait, there's more. So far, we've just been looking at the cost of cost associated with finding bugs. Now, the thing is that the testing is not just about finding bugs. Testing is also, in a sense, a form of insurance. It reduces something that risk management refers to as the cost of exposure. Specifically, it manages the risks associated with quality, which often do have financial consequences. So you think about, there's this economic concept of substitution for those of you who plodded through some economics courses in college like I did. It says that one way to quantify the value of something that's perhaps difficult to quantify is to look at the value of something else that serves as a substitute for it and see if you can quantify that. So basically, insurance is the more typical way of managing risk in the real world, and one which is subjected to the free market, and thus, it's very well established as to how one puts a value on insurance. So the way that the insurance companies establish what the price is that they need to charge for a insurance policy, which which you could say is the actual value of it, right? The actual price charged, which would be above that, would be their profits. The way that the insurance companies do this is through use of what's called an expected payout. The expected payout is calculated by taking the probability of a loss and multiplying it times the cost of that loss. So let's say that you're selling car insurance and you know that 10% of your policy holders will have a claim in a year and that the average claim will be $2,500. So you have to charge each policy holder at least $250 to meet your expected payout. So that's the break-even point for the insurance company. If they charge less than that, they'll lose money. If they charge more than that, they should make money, barring some sort of widespread catastrophe that causes a large number of people to have accidents all at once. So, given this concept of substitution, let's return back to our hypothetical case study here. And we can say, all right, let's suppose that we can estimate some average losses and likelihoods based on some studies of similar organizations. So you say, all right, there's performance problems, we're testing for performance, and organizations like ours, when they have performance problems, they suffer a $100,000 average loss and a 10% likelihood. Functional problems, and you say, that's $5,000 the average loss at a 50% likelihood. Security problems, $250,000, average loss of 5% likelihood. Other kinds of problems, a $10,000 average loss at a 10% likelihood. These are just made up numbers to illustrate the concept here. So the expected payouts then would be 0.1 times 100,000. That's the expected payout for performance problems. 0.5 times 250,000. That's expected payout for security. You got 0.05 times 10,000. That's the expected payouts for functional and so forth. So we come up with 26,000 as our value. Now, I just want to. This is hypothetical, of course, and I want to point out, that your average costs and likelihoods are things that you're going to probably pull off the internet and do some research on. It's based on a pretty small sample of projects, and so this is not a high confidence number. This is really kind of a finger in the air estimate of this. Also, some organizations are less risk averse than others. Some small aggressive startups often are like, well, from great risks come great rewards. So they might not really be terribly concerned about this particular value, more concerned about the bug finding value. I also want to point out that unlike insurance, testers are not going to make the project team whole. Basically, the difference in insurance is a form of risk mitigation or risk management by transference. You're transferring the cost of a problem onto somebody else who agrees to accept it. Testing manages risk through mitigation, basically by taking steps prior to release that are going to reduce the likelihood and or impact of problems after release. So it's a different kind of risk mitigation, but it's still risk mitigation nonetheless. Okay, so again, this is no increased investment here because this testing is already happening. So we're still at an $82,500. So we say that there's basically an additional $26,000 worth of quote-unquote insurance value here, which I've shown here. And so I'm going to add that along with the $32,500 as the benefit. And so again, notice that relatively speaking, this insurance value, the risk mitigation is pretty small relative to the defect detecting value. So that was true also of the non-must-fix bugs that were found. Notice that the contribution was pretty small. And this actually has an important practical lesson for you One of the things that you might want to do if you're going to go off and quantify the value of your testing is you might want to just use cost of quality rather than trying to do this, calculate some of these other values, because they are going to be relatively smaller contributors, and they are also, the techniques for measuring the value is less well established, so it might damage the credibility of your business case. So, be aware of these things, and you can certainly mention them as values, but I'd say that probably if you're going to just try to take a real simple approach, just focus on measuring the cost of quality and leave it at that, and just mention that these other things are also there. But since we're on this topic, let's look at the last of the four things that I mentioned, measurable value, which is the testing information as a guide to project success. So going back to our friend Capers-Jones here, estimating software costs, he identifies poor project tracking as one of the key causes of project failure. So certainly accurate, credible, timely testing metrics would be part of good project information tracking. So if you say medium-sized project, according to Jones's figures, good project tracking will reduce the risk of project failure from 40% to 20%, assuming the testing is kind of half of the project management information picture. Then you can say, okay, 10% of that is the value to the project from testing itself. So let's take a look at what that would mean. Now, I want to point something out here, that the risk of project failure tends to vary quite a bit, as you'll see if you look at his book, Estimating Software Costs. So the value of the information from testing goes up dramatically as the project gets large and complex. Okay, so let's assume that basically we've got a medium-sized project. We're going to reduce the risk through the information generated by testing at 10%. Let's assume that the project cost is the only value that's at risk, which is basically meaning we're ignoring the opportunity cost associated with a project failure. And say, well, if the project fails, we lose all the money that we spent on the project, which is certainly true. So we're going to take the testing budget, the development budget, which are collectively $330,000, and we take 10% of that, so that's the value of the tracking information. So, and take that $33,000 and throw that in the mix here. So I've done that down here. So again, a relatively small incremental increase across these other three values. We've captured less than $100,000 as compared to $500,000 plus of benefit from just the bug tracking. So that's fairly typical that the bug tracking value is going to be the most significant of the values. But still, worth keeping in mind that there is some significant value associated with these other areas outside of bug detection. Now, our overall percentage return on investment here you see is 738%. You might say, okay, well, how's that compared to the real world? Fairly typical number is 800%. There does tend to be tremendous variation in this when we measure it. And we've seen it, down in the 30-40% range, as low as, and as high as in the 3,200% range. So it does vary quite a bit. 800 is pretty typical. So this, while a hypothetical case, is not unusual in terms of the actual number that we see. But, hypotheticals are all well and good. Let's look at an actual case study. Now, this is from a project that my colleagues and I did a few years ago. Let me just try to find this. Shoot. Oops. Bear with me for just one moment here. We're gonna find this spreadsheet and get it open. All right. So you should now see, refreshing on your screen, a spreadsheet. This, by the way, is described in great detail in an article. So it's out on the digital, excuse me, on the basic library or the articles page, one of the two, as a case study in calculating return on investment of testing, and this is described here. So let me walk you through the calculation of the return on investment just for the finding of bugs, must-fix bugs. Okay, so we have the budget for testing. It's $1 million. This is a number that I know. This is the number that was actually spent on testing prior to release. About 10% of the testing effort was spent building test tools and test frameworks and other stuff that had reusable value for the future. So we're going to deduct that out here. This is a form of amortization, basically, and take that out. So that's a long-term asset that was created. We're also going to take out regression test costs. Now, in this case, this is a greenfield development, so all the regression testing was basically retesting functionality that had already been tested in that project but had to be retested due to the extent of changes that occurred. That's a cost of internal failure, so we need to move that somewhere else. So just the detection costs is $1 million minus $100,000 minus $500,000, or $400,000. That's our net detection cost. Now, we found 1,500 must-fix bugs before testing, and that means that our approximate cost per bug is $267 per bug. So that's just 400,000 divided by 1,500. Okay, now internal failure costs. A couple things here. First, let's do the easy one. The regression test costs, right? That's just the same number that was up here, moved down there because it's an internal failure cost. And then there were 30 developers during the 3-month system test period that were doing pretty much nothing but fixing bugs. And so assuming a fully burdened salary rate of $100,000 per year, which was fairly typical at that time, that gives us $750,000 in bug fix costs. Now, this is something that's worth pointing out, that notice that some of the costs of internal failure are not testing costs; they're development costs, and that's going to be that's going to be typical. You're going to need to account for that. So you need to have some way of estimating the amount of developer effort associated with the with internal failure. So our net internal failure costs, $1.25 million. Take $750,000 plus the $500,000. Again, must fix bugs found prior to testing, 1,500, or found during testing, excuse me. So our approximate cost per bug is $833. Okay, so our total cost for bug found during testing now would be the cost of detection plus the cost of internal failure would come to $1,100. So notice that as long as the cost of an external failure is greater than $1,100, we've broken even or better on our testing. So that's good. Now let's see if we can figure this out. So sustaining costs in the first 6 months prior to release, the organization spent about $3 million. Sorry, the first 6 months after release, the organization spent about $3 million on sustaining costs. So that's developers, testers, and tech support people. And according to my discussions with the client, about 50% of that was bug related, and the other 50% of the sustaining cost was adding new features. So that means that our external failure costs are $1.5 million. Notice that to do this, you'd have to know the size of the entire team supporting the release, supporting the product, and you have to know about what percentage of the effort is bug related, and then you want to avoid assuming too long a period of value. You know, you got a rapidly evolving product, and it's going to change pretty substantially within 6 months to a year. You know, you don't want to try to count a lot of value of saved cost of external failure after that initial period is up. So that's why I assume 6 months. And so you want to have a discussion with people about this when you're building this model of what's a reasonable period of time over which the bug benefit is going to accrue, essentially. There were 500 must-fix bugs found after testing, after release, and so that's cost per bug of $300,000 or $3,000, excuse me. That's the cost of external failure on average per bug, which, as you can see, is considerably above the cost of internal failure and detection, which was, again, $1,100. So we can calculate the return on investment. Basically, there are a few ways that you can do it. You could take the difference, which would be 3,000 minus 1,100 or 1,900, and multiply it times the 1,500 to get the net benefit. That'd be this 2.85 million that you see down here. Another way to calculate this net benefit of testing is to take the cost of quality with the testing, which is the cost of detection, cost of internal failure, and the cost of external failure, adding those three things up, and then calculating what the cost of quality would have been if there hadn't been any testing, which is just the number, the cost per bug for external failure, plus the number of bugs found after testing, plus the number of bugs found during testing. So 2,000 times 3,000, which would be 6 million. So you get two ways to calculate that. And so we can come up with this net benefit of 2.85 million on an initial investment of the cost of detection, which is, as I said before, is 400,000, as you see here. So that's 400,000, and then try to drag this down just a little bit. Let me turn off the ribbon for the moment. Right. 400,000 as our net detection cost versus the 2.85 million net benefits, 713%. So, you know, fairly typical return on investment, just calculated based on the value of bugs found. And I did continue this on for some of the other ones, the unfixed bugs, the past tests, the value of advice. I'd encourage you just to read the article if you're curious about that, because, you know, again, in this real world case, we also saw that, as in the hypothetical, the majority of the value was from the finding of must-fix bugs. Okay, now let's get back over to the presentation here. Sorry, this takes a moment. Go to webinar is not necessarily the most graceful beast when it comes to switching screens. Okay, so that's the case study. Yeah, so definitely, you know, do try this at home. This, as you see, is nothing. There's no math more complicated than what you learned by the 4th grade involved here. It's, you know, addition, subtraction, multiplication, division, real straightforward stuff. I bought a book on measuring quality return on investment at one point, and within like the 2nd chapter, this guy was already off into partial differential equations and all of this nonsense, and I just put the book down, didn't even bother to finish it, because, you know, for one thing, I can barely remember that stuff, and I would have to spend, you know, days and days refreshing my memory as to how that worked, and I don't remember enjoying it that much in college, even when I did know how to do partial differential equations. The other thing is, other people don't know that stuff too. You know, I mean, it's, you know, go into client's office or your boss's office and start talking about partial differential equation this and, matrix inversion that, he's going to look at you like you're from Mars, and your credibility is just going to go shooting out the door, because he's going to think, this guy has come in here to flim-flam me with math I don't understand. So I think there's some real value in keeping this super simple, something that you can do really easily. Everybody can understand it. It can be encapsulated in a spreadsheet, and you can have discussions about how that came about. I remember the last assessment I did, we sat around and talked about just this question of how efficient is the test team and where is the value coming from, and we walked through this spreadsheet, and it was clear to everybody how it was being measured, and we made some assumptions that they thought, well, I don't know if those are right, let's go validate those assumptions. So really, to the extent that you can keep this nice, transparent, and simple, not only will it be a lot easier for you to do, it's going to be a lot easier for you to get people to believe. So, yeah, this here's the case study that I was alluding to. Detailed walkthrough on the technique in the case study, basic library, rbcs-us.com. So you go to the resources page, and on the resources page you can access the basic library. The article is called Testing ROI, What IT Managers Should Know. So give it a try and see what you find. I think you're going to find, I'm very confident you're going to find that you are actually saving your company money, which is good. You're a savings center, and I bet most organizations don't know that, and I bet yours is probably one of them. So this is an opportunity to spend an hour or two doing some conversations with people and some quick calculations and so forth, and you can come up with a finding that is very revealing to you and to other people in the organization. Okay, I'm going to put up the advertisement here while we go through the Q&A process. We have now made it successfully through the end of the presentation without the office flying off to Kansas, as it sort of seemed like it was about to do at multiple points in time. We still have sideways rain going on out there, but we're here, safe and sound. So let me get this question panel open here and undock this thing. I can actually read it. Still kind of dealing with learning this change they made to the GoToWebinar interface as respect to the questions. Okay, great. I was hoping somebody would ask this question, and Rich did. How is the ROI insurance paradigm applied away from the waterfall world, especially in agile frameworks where everything is a sticky note on a whiteboard? Is the return here measured in terms of more accurate downward burn down charts collectively at the sprint of sprint levels? Well, yeah, I mean, you're putting your finger on one of the challenges of doing this in an agile world, which is like, do we have adequate metrics, and does the value added by testing change? So notice that one of the primary metrics that we needed to have was some sort of count of must-fix versus non-must-fix defects. Now, that can come out of a database like Bugzilla, or that can come out of hash marks made at the bottom of a whiteboard as a sprint continues. It doesn't really matter as long as I've got some amount of detail on that that can be put into a spreadsheet and ultimately used as a calculation. The whole insurance value of testing, I don't believe that actually changes much in an agile world. Ultimately, we're talking about confidence building and risk mitigation, right, which is a question of stuff we've covered. So that value would remain the same. Now, I think one of the things about Agile is if the developers do really well in terms of upfront removal of defects,